Hello students, hope you all are doing well. In the previous lecture, we have discussed about image smoothing using frequency domain filters. So now in today's lecture, we will discuss about image sharpening using filter domain filters. So in previous we showed that an image can be smoothed by attenuating the high frequency components of its Fourier transform because its edges and other changes in intensity are associated with the high frequency components. Image sharpening can be achieved in the frequency domain by high-pass filtering, which attenuates the low frequency components without disturbing high frequency information in the Fourier transform. So all filter functions of HUV are understood to be discrete functions of size p into q. That is, the discrete frequency variables are in the range u is equal to 0, 1 to up to p minus 1 and v is equal to 0, 1 to up to q minus 1. So a high pass filter is obtained from a given low pass filter using the equation HHP into uv is equal to 1 minus HLP uv, where HLP-UV is the transfer function of the low pass filter. So we consider ideal Butterworth and Gaussian high pass filters. As in the previous section, we illustrate that the characteristics of the filters in both the frequency and spatial domains. So here a 2D ideal high pass filter IHPL is defined as HUV if DUV is less than equal to D0 then 0, and if DUV is greater than D0 then it is 1. So here D0 is the cutoff frequency and DUV is given by the equation. So this expresses the directly from the IHPF is the opposite of the ILPF in the sense of that is it is set to 0. All frequencies inside the circle of radius d0 while passing without attenuation all frequencies outside the circle. So as in the case of the ILPF, the IHPF is not physically realizable. So we consider here for completeness and as before because its properties can be used to explain phenomena such as ringing in a spatial domain. So here this figure shows the typical 3D plots, image representations and cross sections for these filters. So we see that Butterworth filter represents a transition between the sharpness of the ideal filter and broad smoothness of the Gaussian filters. And this figure in this illustrates what these filters look like in a spatial domain. So here this figure consists of various IHPF results using the original image in the above figure, which in that D0 set to 30, 60 and 160 pixels respectively. So the ringing is to server it is produced to distorted, thickened and object boundaries. So edges of the top three circles do not well because it is they are not strong as the other edges in this image. So it is giving of smaller magnitude. So it is looking at a spot size of the spatial representation of IHPF here in this figure, and keeping in mind that the filtering in the spatial domain is convolution of the spatial filter with the image helps explain why the smaller objects and lines appears almost solid white. So here figure A, we can see the situation improves somewhat with D0 is equal to 60. So the edge distortion is quite evident still, but not now. We begin to see filtering on the smaller objects due to the now familiar inverse internship relationship between the frequency and spatial domains. So we know that the spot size of this filter is smaller than the spot of the filter with d0 is equal to 30. So the result for d0 is equal to 160 is closer to what high pass filtered image should look like. So here the edges are much cleaner and less distorted, and the smaller objects have been filtered properly. So the constant background in all images is 0 in these high pass filters images, because high pass filtering is analogous to differentiation in the spatial domain. Now 2D Butterworth high pass filter BHPF in of order n and cutoff frequency d0. So it is defined as HUV is equal to 1 upon 1 plus d0 upon duv raised to 2n. So here duv is the expression. This expression is follows the directly from the above equation. So the middle row of this figure shows the image and cross section of the BHPF function. So as with the low pass filter, we can expect Butterworth high pass filters to be have smoother than IHPFS. So this figure shows the performance of a BHPF of order 2 and with D0 set to the same values. So the boundaries are much less distorted than the above figure, and even for the smallest value, the cutoff frequency. So the spot sizes in the center areas of IHPF and the BHPF are similar. So the performances of two filters on the smaller objects is comparable. So the transition into higher values of cutoff frequencies is much smoother with the BHPF. Now Gaussian high-pass filters. So the transfer function of the Gaussian high-pass filter with cutoff frequency locus at a distance d0 from the center of frequency rectangle is given by HUV is equal to 1 minus e raised to minus d square into uv upon 2 d0 square. So duv here this expression follows directly from the here, the third row, which shows a perspective plot, image and cross section of GHPF function. So the same format as for the BHPF. So we can show in this figure. Here it is comparable results using GHPFs. So as expected, the results obtained are more gradual than with the previous two filters. So here this figure is a 1026 into 962 image of a thumbprint in which smudges are evident. So key step in automated fingerprint recognition is enhancement of print ridges and the reduction of smudges. So enhancement is useful also in human interpretation of prints. So in this example, we use a high-pass filtering to enhance the ridges and reduce the effects of smudging. So enhancement of ridges is accomplished by fact that they contain high frequencies which are unchanged by a high-pass filter. So on the other hand, the filter reduces low frequency components which correspond to slowly varying intensities in the image, such as background and smudges. So here, figure B is the result of using Butterworth high-pass filter of order 4 with a cutoff frequency 50. So, the high-pass filtered image lost its gray tones because the DC term was reduced to 0. The net result is the dark tones typically predominate in high-pass filtered images, thus requiring additional processing to enhance details of interest. So, a simple approach is to threshold the filter image. We can see figure C, which shows the result of setting to black all negative values to the white all positive values in the filter image. So Note here how the ridges are clear and the effect of the smudges have been reduced considerably. So ridges are barely visible in the top right section of the image. So it is nicely enhanced in the last image. So now the Laplacian in the frequency domain. So we used the Laplacian for the image enhancement in the spatial domain. So in here we revisit the Laplacian and so that it yields equivalent results using frequency domain techniques. So it can be shown here that Laplacian can be implemented in the frequency domain using the filter HUV is equal to minus 4 pi square into U square plus V square. So with the respect to center of the frequency rectangle using the filter HUV is equal to minus 4 pi square into U minus P by 2 raised to square plus V minus Q by 2 raised to square is equal to minus 4 pi square into d square of uv, where duv is the distance function and the Laplacian image is obtained as del square fxy is equal to inverse form of huv fuv. So fuv is the dft of xxy. So here enhancement is obtained as g of xy is equal to fxy plus c del square fxy. Here c is equal to minus 1 because HUV is negative. So the frequency domain is written as the gxy is equal to inverse form of FUV minus HUV FUV, inverse form of 1 minus HUV into FUV, and so we can get inverse form of 1 plus 4 pi square d square UV into FUV. So this result is elegant. So it is the same scaling issues just mentioned, compounded by the fact that the normalizing factor is not easily computed. So here in this figure A is the same as the figure 3.38. You can see that in the book. And this figure B here, figure B shows the result of in which the Laplacian was computed in the frequency domain. So scaling was done as described in the connection with that equation. So we can see by comparing this figure that the frequency domain and spatial results are identical visually. Now the Unsharp masking, Highboost filtering and high frequency emphasis filtering. So using the frequency domain methods, the mask is defined as G mask into xy is equal to f of xy minus FLP of xy, with FLP of xy is equal to inverse form of HLP upon into UV FUV. So here HLP is equal to into xy is equal to inverse form of HLP UV F of UV. So HLP UV is the low pass filter and FUV is the Fourier transform of fxy. So here FLP xy is smooth image analogous to f bar xy in this equation. Gxy is equal to fxy plus k into g mask sy. So g of xy is equal to inverse form of 1 plus k into 1 minus HLP UV into FUV. So we can get inverse form of 1 plus k into HP of UV into F of UV. Here if k1 is greater than is equal to 0 gives the controls of the offset from the origin and k2 is greater than is equal to 0 controls the contribution of high frequencies. So we can get here g of xy, which is inverse form of k1 plus k2 into hp of uv f of uv, where k1 is greater than is equal to 0 and k2 is greater than is equal to 0. So here in this figure, which is shows 416 into 596 chest, 416 by 596 chest X-ray with the narrow range of intensity levels. So the objective of its example is to enhance the image using high frequency emphasis filtering. So here figure B shows the result of high-pass filtering using the Gaussian filter with D0 is equal to 40, which is approximately 5% of the short dimension of the padded image. So the filtered result is rather than featureless, but it shows faintly the principal edges in this image. So here this figure C shows the advantage of high emphasis filtering, which we used with K1 is equal to 0.5 and K2 is equal to 0.75. So figure D shows was indeed an approximate method to further enhance the image. So here the bone structure and other details that simply are not visible in any of the other three images. So the final enhanced image is the little noisy, but this is typical of X-ray images when their grayscale is expanded. Now homomorphic filtering. So the illumination reflection model, which is introduced in unit 2, which is used to develop a frequency domain procedure for improving the appearance of an image by simultaneous intensity ranges compression and contrast enhancement. So image fxy can be expressed as the product of the illumination I of xy and reflectance, which is r of xy components. So fxy is equal to I of xy into r of xy. So this equation is cannot be used directly to operate on frequency components of illumination and reflections, because the Fourier transform of a product is not product of a transform. So formation of fxy is equal to f is not is equal to a formation of I into xy into r into xy. So z of xy is equal to in f of xy is equal to in I of xy plus in r of xy. So we can get formation of z of xy, which is equal to formation of in fxy is equal to formation of in I into xy plus formation of in r xy, which is z, or we can get z of uv is equal to fi of uv plus fr of uv, where fi uv and fr uv are the Fourier transforms in I of xy and in r of xy respectively. So we can here filter z of uv using the filter huv, so that suv is equal to h of uv into z of uv, which is h of uv into fi uv plus h uv plus fr uv. So we can get here I in I dash xy plus r dash xy. So finally we can get g of xy is equal to e raised to s of xy is equal to e raised to I dash xy into e raised to r dash xy is equal to I0 of xy r0 of xy. So which are the illumination and reflectance components of the output, which is the processed image. So here the filtering approach just derived here we can see that in this figure. So this method is based on a spatial case of a class of a system known as homomorphic system. In this particular application, the key to the approach is the separation of the illumination and reflectance components achieved in the form. So the homomorphic filter function HUV then can operate on this component separately. So the illumination component of an image is generally characterized by the slow spatial variations, while the reflectance component tends to vary particularly at the junctions of dissimilar objects. So these characteristics are linked to associating the low frequencies of the Fourier transform of logarithm of an image with illumination of high frequency with reflectance. So here this figure shows the cross section of such a filter. So if the parameters gamma L and gamma R gamma H are chosen so that gamma L less than 1 and gamma h greater than 1. The filter function in this figure tends to attenuate the contribute made by the low frequencies and amplify the contribute made by the high frequencies, which is reflectance. So the net result is simultaneously dynamic range compression and contrast enhancement. So the shape of the function in this figure can be approximated using the basic form of high-pass filter. For example, using a slightly modified form of the Gaussian high-pass filter yields the function h is equal to h up into uv is equal to gamma h minus gamma l into 1 minus e raised to minus c into d square of uv upon d0 square plus gamma l. So here the c is which is constant, so the c controls the sharpness of the slope of the function as it transitions between gamma L and gamma H. So this filter is similar to the high emphasis filter. So to attenuate the contribution made by illumination and amplify contribution made by the reflection. So here this figure shows a full body PET, means positron emission tomography, which is a scan of size 1162 into 7 by 746 pixel. So the image is slightly blurry and many of its low intensity features are obscured by the high intensity of the hotspots, dominating by dynamic range of the display. So here figure B shows the how much sharper and hot spots the brain and the skeleton are in the processed image and how much more detail is visible in this image. So by reducing the effects of the dominant illumination components, it becomes possible for dynamic range of its display to allow lower intensity to become much more visible. So the enhanced image in figure B is the significant improvement over the original. So here this figure is the original image, which is A. So A is the original image and image B is the image processed by the homomorphic filtering. So not details inside shelter. Thank you.